So today we have the pleasure of welcoming Emily Levesque. Emily is a professor at the University of Washington, and her work has really been illuminating the late-stage evolution of massive stars, and all the interesting sort of outcomes that might come after that. So a little bit on Emily's academic history. She, before her time at the University of Washington, you were a postdoc at the University of Colorado, and you did your PhD at the University of Hawaii. This is something that I've had a tiny bit of experience with, but Emily is the author of two graduate level textbooks, one on red supergiants, one on stellar evolution. And the stellar evolution one is my new favorite stellar evolution book. Emily and her research have been honored with sort of more awards than we can sort of list in a 1-hour colloquium. But in the past year, she has been given a gold medal of honorary patronage at Trinity University, and she's a 2019 Cottrell Scholar. And because we're here at Harvard, she's been in the past an Annie Jump Cannon Award winner from the AAS. So with that, I'll actually let you give your talk, and thank you so much for visiting us.
Great. Thank you very much for inviting me. So you mentioned the two books that are both published through the AAS IOP ebook series. So both the Red Supergiant book and the Understanding Stellar Evolution book are free to anyone that has an institutional subscription, and that's where this image is from. This is stolen off the cover art of my Red Supergiant book. So what I'll be talking about today is a lot of the research that me and my group have been doing on red supergiants and the way that we can use observations as a way of testing stellar theory. So this magnifying glass quote comes from a quote in Kippenhahn and Weigert where they describe late-stage stellar evolutionary phases as magnifying glasses. I think they describe them as ruthlessly revealing the errors in earlier phases of evolution when people try to model them. So a lot of this work has been done with people from the UW Massive Stars group. So this is everybody that has been in the group. There have been a couple updates. So Jamie Lomax was a postdoc at UW. She's now faculty at the US Naval Academy. Aislinn Wallach is now in grad school at BU, and Locke is now in grad school here. And all of the people that I'm showing have contributed to the research that you'll be seeing here, and I'll be highlighting their contributions as we go. So I figured I would start with a reminder of what red supergiants are. So if you take the HR diagram and you populate it out with stars, you see the main sequence that we all know and love. You see the giant branch, so the late evolution of solar mass and low mass stars. And then you see the fairly horizontal evolution across the top of massive stars, so about 8 solar masses or more. And this is the regime that we're focusing on when we talk about red supergiants. If we zoom in, we can check out how red supergiants evolve and how they behave. They're the helium-fusing evolved descendants of moderately massive stars, so around 10 to 40-ish solar masses on the main sequence. What you'll have is a main sequence star that is happily going about its life, fusing hydrogen, runs out of hydrogen and gets very upset, and switches to fusing helium. When this happens, just according to the basic relationship between luminosity, radius, and temperature, the star's luminosity will stay fairly constant, but it will begin streaking across the HR diagram as it starts to pursue helium fusion. It'll briefly pause as a yellow supergiant for only about 10 to 100,000 years, and then eventually hit a stable helium-fusing state where it is a red supergiant. So these are the coldest massive stars that we know. They're the physically largest that a massive star will get during its lifetime. An important distinction is that they are different from red giants, despite the really unfortunately similar names. They have much higher initial masses, they have shorter lifetimes, and they follow completely different evolutionary pathways. So they're observationally sometimes almost indistinguishable, and I'll talk about that in a little bit, but they're very distinct in terms of their evolution. And then finally, they can be an end phase or an intermediate phase in massive star evolution. So some red supergiants will sit here and then eventually explode or undergo direct core collapse. Sometimes these will produce things like type 2p supernovae. Sometimes their outer layers will be stripped away thanks to stellar winds, and they'll go scooting back across the HR diagram to like somewhere on this wall and become Wolf-Rayet A stars before then presumably dying. We can trace out how we think a star like this behaves over the course of its life with an example of one of these, an evolutionary track. If we look at a theoretical HR diagram where we're summarizing all massive stars' evolution with evolutionary tracks, you can get a sense of what red supergiants will look like from the outside. Red supergiants land in this very narrow strip of the HR diagram right about here. They're obeying the Hayashi limit, so this opacity, basically restriction on how cold the stars can stay while remaining hydrostatically stable. So they're in this relatively small region. The right sides look fairly similar at a first glance. Things get worse when you look at the interior. So this is an old Kippenhahn diagram that we tried to update for our textbook by color coding it. So red is helium, hydrogen fusion, blue is helium fusion, green is everything else. But you can see that this would start as a main sequence 15 solar mass star while core hydrogen fusion was going on. And then by the time it becomes a red supergiant, you have this very huge convective region above the hydrogen fusing shell and helium fusing core. What this means when you stick all of this together is that the outside of a red supergiant is really going to look something like this. The extremely cold and puffy atmospheres give you this really huge scale height, so you get convective cells that are on the order of the radius of the star inside. It makes it look like the whole star is just kind of boiling as it sits there in a presumably stable state. So, red supergiants are cool literally and cool figuratively, but I always try to make the argument of who actually cares about this one little weird niche of massive star evolution. And I would argue that you do. Everybody in the room cares about red supergiants. If you're interested in any aspect of stellar evolution, if you're interested in dust production, massive star populations in the early universe, transients, gravitational waves, any of these subjects ties back to red supergiants and understanding what their physical properties are, how they evolve, and then eventually what they make. So this is hopefully making the argument that they're important to understand. And what I wanted to spend most of this talk on was highlighting a few challenges that we're currently facing in terms of how red supergiants work. So the first one that I want to highlight is understanding the temperatures of red supergiants. I'd highlighted this region of the HR diagram before where red supergiants are supposed to sit. To the right of this is a sort of forbidden zone on the HR diagram where you shouldn't be able to observe a star if it's hydrostatically stable. About 20 years ago, when we were first putting red supergiants on the HR diagram, they all landed in the bad place. So none of them were remotely agreeing with predictions of stellar evolution and stellar theory, so we all immediately blamed the theorists and said, well, you must be doing this wrong. Surely stars can't work like this. And it took years before someone finally pointed out that the way that we were measuring their temperatures was kind of sketchy. We were largely basing it off the stars' colors, ignoring the fact that these stars have big, broad emission lines and dust complicating things. And we were mostly observing nearby red giants and then just sort of lowering the temperatures a little bit and saying, we're good. What my very first research project was trying to revise these temperatures. And we did it with these new, improved models of red supergiant atmospheres from the Marks group that wound up showing us what their spectra would look like as a function of temperature. So a red supergiant can range from a K-type star, where this is roughly what the optical spectrum would look like, to a late M-type star where the spectrum is dominated by titanium oxide bands. So you can watch how this spectrum evolves as we move this slider from early K to late M, and we drop the temperature from about 4,000 Kelvin down to 3,500. So as you lower the temperature, you're able to form more titanium oxide in the star's atmosphere. The titanium oxide absorption bands get much stronger, and they can basically serve as thermometers in red supergiant atmospheres. They're wonderful gauges of the star's temperature. So using these models and using spectrophotometry of about 75 red supergiants in the Milky Way, we tried to remeasure all of these temperatures to see if that help matters. And all the temperatures moved from here to here. So the theorists were right, we'd fixed the problem, and we now had a great understanding of red supergiant temperatures, sort of. There's some asterisks on this. This gets difficult in metal poor galaxies. As you have less titanium oxide, sometimes the effect will sort of saturate, or it'll be more difficult to identify the stars that are really in a red supergiant state. This technique is also limited to the optical. If we do temperature measurements in the infrared, they don't quite match, and we currently have very limited data on how to get good temperatures in the IR. And getting spectrophotometry of individual stars is really costly. It would be great if we could find better methods. So this is something that my group's been exploring in the last couple of years. Brooke DeCenzo actually started working with me as a high school student, and they're now an undergrad at UW. And this was an attempt to take red supergiant observed data, which is in black, and different Marx model data, which are the different colored lines corresponding to different surface gravities, and see if we could find atomic lines that would work well as temperature gauges, something like titanium or iron. Neither titanium nor iron work very well. Any temperature effect starts to saturate when the stars get this cold. You move into like the region where collisional excitation starts to become a problem. This is a plot of the calcium triplets, sum equivalent widths as a function of temperature. The calcium triplet is sensitive to just about everything. It's a function of luminosity, it's a function of surface gravity, but it is also a function of temperature. And it seems to be a decent gauge of how you can measure the temperature in a star if you have a grasp on surface gravity or a grasp on other parameters, which you can get from other narrow lines. What's exciting about this is that the calcium triplet is going to be observed intensely with Gaia. So if we can refine this to be a good temperature gauge, then we can start measuring temperatures on really large scales with Gaia data. What would be even better is if we could use photometry to measure red supergiant temperatures, and we are getting better at this. V minus K colors, where you go from the middle of the optical all the way out into the far near IR, work pretty well, and I'll talk more about attempts to try and use temperature gauges later on in the talk. Another appeal of red supergiants is that they're really luminous, so they're very easy to observe in other galaxies. We have these gorgeous extragalactic samples of red supergiants throughout the local group, even beyond the local group, and sampling these gives us a chance to look at massive stars at other metallicities, try to sample a population